Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Clausius theorem and Clausius inequality. Let's begin. Clausius theorem, which is known as the change of entropy in a reversible process. The statement is, according to that of Clausius theorem, it states that in any reversible cycle, the net change in entropy is 0. So, mathematically we can write here, in any reversible cycle the change in entropy will be 0, and that can be written like this: the closed curve integration over dq by t is equal to 0. Del S, that is the change in entropy, dq, that is the change in heat, T with the temperature. We have to prove that statement. How to prove? To prove that one, we have to consider a reversible process. So, we know Carnot cycle is a reversible cycle. To prove that one, we have to consider Carnot cycle, Carnot's reversible heat engine. In Carnot's reversible heat engine, this is the PV diagram, pressure, here is the volume, and Carnot's reversible cycle is given like this. That is A, B, C, D. A Carnot cycle has two isothermals and two adiabatic processes, in which isothermal processes it has one isothermal compression and another isothermal expansion. In case of adiabatic processes, it has one adiabatic expansion and another one is adiabatic compression. So, in this way the Carnot's reversible cycle looks like. Here we consider A, B, C, D as Carnot cycle having two isothermals, A, B and C, D are two isothermals, and two adiabatics, B, C and D, A are two adiabatics. So, here is isothermal expansion, here is isothermal compression, here is adiabatic expansion, here is adiabatic compression. So, we have to calculate what should be the change in entropy during that of entire Carnot cycle. So, we have to consider one by one cycle and then combining all these three. So, during isothermal expansion AB, right here, during isothermal expansion AB, what happened? The working substance takes Q1 amount of heat from the source at constant temperature T1. Therefore, the increase in entropy, increase in entropy of working substance is given as, that is Q1 divided by T1. Here is the isothermal expansion AB. Now in that of case, this case also decrease of entropy of that of source. Here this also decreases the entropy. Entropy of the source. Now during adiabatic expansion BC, what happened? No heat is taken in or given off, hence change in entropy is 0. This is AB isothermal expansion. Now in BC, that is adiabatic expansion, what happened? During adiabatic expansion, BC, what happened? No heat is taken in or given up. No heat is taken in or given up. So what happened here? Hence change in entropy will be 0. Change in entropy is equal to change in entropy is equal to 0. Here change in entropy is Q1 by T1. Here change in entropy will be 0. Again this one is the isothermal compression, this one is the adiabatic compression. So what happened during that of adiabatic compression? Here CD, during this is the isothermal compression, just I write here, that is isothermal processes, isothermal, that is isothermal, that one is the adiabatic, that one is the adiabatic. Here is the expansion, here is the compression, here is the expansion, here is the compression. Okay. Now CD, that is the isothermal compression, what should be the change in entropy? So during isothermal compression, CD, the working substance gives off Q2, gives off Q2 amount of heat to that of sink, amount of heat to the sink at constant temperature T2. Therefore decrease in entropy of that of working substance. Therefore decrease in entropy of working substance will be how much? That is Q2 divided by T2. Again in adiabatic compression, what happened? There will be no such heat, so the change in entropy will be 0 here. So in that case, when decrease in entropy, what happen? This also increase in entropy of the sink. At that particular case, this also increases this also increases entropy of the sink. Now in adiabatic compression, during adiabatic compression, dA, there is no change in entropy. There is no change in entropy. So look here, in isothermal compression, change in entropy will be Q1 by T1. Adiabatic isothermal expansion, that is Q1 by T1. Adiabatic expansion, that will be 0. Isothermal compression, that is Q2 by T2. Again adiabatic compression, that will be 0. Hence during the whole Carnot cycle, what should be the net change in entropy? Hence during whole Carnot cycle, it will be the net change in entropy, of working substance is equal to, that is del S closed curve integration over dq by T. So del S is equal to summation over, that is Q1 by T1 minus Q2 by T2, that is Q1 by T1 minus Q2 by T2. Here we use the sign convention, since that is the increase in entropy taken as positive, decrease in entropy taken as negative sign. That is, this is also known as, the net change in entropy of the source sink system. Now we know from that of reversible cycle what happened, but for reversible cycle, Q1 by T1 is same as Q2 by T2. So del S will be how much? 0. Therefore change in entropy del S is equal to, that is closed curve integration over dq by T is equal to 0, or we can say del S is equal to 0. That is change in entropy in a reversible cycle is 0, as the statement indicates. We take a reversible cycle as Carnot's heat engine, Carnot cycle, and prove it change in entropy will be 0. Now we have to generalize that particular statement, that particular mathematical equation. How we have to generalize this. So here that statement indicates the net change in entropy, here that is the net change in entropy of the working substance and also the surroundings, during a complete Carnot cycle is 0. During a complete Carnot cycle is 0. That from that of equation. Now we have to generalize that particular equation. To generalize that one, we have to consider a reversible cycle which is made up of a number of elementary Carnot cycle. So let I take here the PV diagram in axis pressure, in that of axis, that is volume. We take a reversible cycle here. Let that reversible cycle be A, B, C, D here. And it consists of the number of elementary Carnot cycles as here a number of elementary Carnot cycles these are the elementary Carnot cycle. Look at these cycles here. Let A, B, H, D, E, F, let L, C, G, K, O, this is let I, J, N, P. These are the namings. So in these cycles, the paths like BH, FL, JP and so on, this path are traversed twice in the reverse order. Why? If we take that elementary Carnot cycle, what happened? The direction will be this. If I take that Carnot cycle, here the direction will be just its opposite. So during each path the reverse order executed. That's why they cancelled with each other. So the net effect of that of whole process is that the substance goes along the closed zigzag path. That's why for each elementary Carnot cycle we can write the equation. This is the in generalized way. In general, we consider that one. For each elementary Carnot cycle, the equation can be written as del S is equal to del Q1 by T1 plus del Q2 by T2. That will be how much? That will be 0, since one is absorbed, another one is rejected, one is increased, another one is decreased. So in case of increase I use the positive sign, in case of decrease I use the negative sign. As a whole this is same as that, so the result will be 0, or we can write here del S is equal to del Q by T is equal to 0. Adding the change in entropies of all the elementary Carnot cycle. What happened here? Adding the change in entropy of all the elementary Carnot cycle del S is equal to summation over del Q by T, that will be 0. If all the elementary Carnot cycles are close to each other, then the zigzag path will coincide with that of smooth curve A, B, C, D. So if all the elementary Carnot cycles are close to each other, then the zigzag path will coincide smooth curve A, B, C, D. Just we write, therefore the change in entropy del S, the closed curve integration over dq by t is equal to 0. Hence the theorem in any reversible cycle the net change in entropy, the net change in entropy is 0, which proves that Clausius theorem. This proves the Clausius theorem. Clausius theorem now proved. Means the change in entropy in any reversible cycle is 0. This is here the Clausius theorem, that is the statement, and we prove it. Change in entropy will be 0. We are taking this in case of in a generalized way, finally prove that one. Now what should be the change of entropy in an irreversible process? Now we have to derive change of entropy entropy in an irreversible process. This can be proved or this can be derived by using Carnots theorem. In Carnots theorem, we know the efficiency of reversible heat engine is more as comparison to that of irreversible heat engine. From Carnots theorem, the efficiency of reversible heat engine is greater than the efficiency of irreversible heat engine. Eta R is the efficiency of reversible heat engine, eta I is the efficiency of irreversible heat engine. So, eta R, that is 1 minus T2 by T1, where T1 and T2 are the two temperatures in which the source and sinks acted, and again for that of eta I, that is 1 minus Q2 by Q1. Here we can say in that of reversible cycle, it is absorbing Q1 amount of heat at temperature T1 from that of source, and Q2 amount of heat is rejected to that of sink at temperature T2, and here that irreversible heat engine or reversible heat engine both are treated at the same temperature T1 and T2. These are the formula of efficiency of these two heat engines. Now, Q2 by Q1 therefore Q2 by Q1 is greater T2 by T1, T2 by T1. Now, Q2 by T2 is greater Q1 by T1, and to that side, so it will be Q2 by T2 minus Q1 by T1 greater 0, means that quantity will be positive. In the given irreversible engine, the source loses the entropy by an amount Q1 by T1 and sinks gains that amount of entropy, that is Q2 by T2. So, the net change in entropy of that of working substance is 0, because when the cycle is completed, the working substance returns to its initial state. Therefore, what happened here? The net change in entropy of that of system in the irreversible process will be how much? The net change in entropy change in entropy of the system in the irreversible cycle is what? Del S is equal to, that is Q2 by T2 minus Q1 by T1, which is greater than equal to 0. That is, what is Q2 by T2 and Q1 by T1. So here in case of that irreversible heat engine, what happen? The source loses the entropy by an amount Q1 by T1 and the sinks get the entropy, that is Q2 by T2. So the net change in entropy of that working substance becomes 0 during a complete cycle. So here the change in entropy will be that much, which is greater than equal to 0. Hence the entropy of the system increases during an irreversible process, that is the irreversible process, and the entropy is greater than that of 0. So in general we can write, del S universe is greater than equal to 0. That is the entropy, principle of entropy, or that equation basically known as Clausius inequality. Clausius inequality. Here the equality holds for reversible process. In reversible process, del S is equal to 0, and the inequality means del S greater than 0 is for irreversible process, and universe stand for the system plus surroundings. System plus surroundings, overall we can say that is the universe. So that equation indicates del S is equal to 0 for reversible process, del S greater than 0 for that of irreversible process, as we get here del S is greater than 0 for irreversible process, and universe stands for system plus surroundings. The overall change of entropy, that means the system plus surrounding will be 0 or greater than to that of 0. Here is the change of entropy in an irreversible process and Clausius inequality. So with the help of this video lecture we understand what is Clausius theorem, or we can say the change of entropy in reversible process. So in reversible process the change of entropy will be 0, and it can be proved by using the reversible cycle as Carnots heat engine cycle. We get change of entropy will 0, and generalizing that one we take the elementary Carnot cycles here and summing these cycles, and finally we get the change of entropy again will be 0, which is Clausius theorem. Now we have to prove or derive what should be the change of entropy in an irreversible process. We use the Carnot's theorem here and finally get in irreversible process the change of entropy will be greater than 0. So in generalizing all these things we say del S inverse, that is change of entropy of system plus surrounding, which is greater than equal to 0, which is known as Clausius inequality. So with this useful and informative notes, let me wind up this session. Thank you.